Hello, welcome to this video lecture presentation on engine control system for SI engine, presented by Professor B. Ashok, working in VAT University in India. Let's enter into the presentation. Introduction. Basically, this topic is covering about the electronic management system of an SI engine. Electronic management system or a engine management system is nothing but a typical microcontroller based system which is controlling the operation of SI engine. This type of electronic control to the engine is applied to in the year of 1980s, in the beginning of 1980s, basically to reduce the emission and as well as to improve the performance of an engine operation. So for that the researchers has been thought to introduce an electronically controlled system in order to meet the emission norms and the performance norms. Also to deal with the other control functions like other control functions. If you will see in this picture, the right side of the picture shows the block diagram of an SI engine, which is consist of a piston arrangement and arrangement with intake valve and exhaust valve, and along with the turbocharger and the intake systems. And the right side of the left side of the picture shows the engine management system. The engine management system consists of a number of internal components. Basically, you might be already seen or you might be already have and came across with the number of series of lectures related to the electronic fuel injection system. Of course, this lecture is also related towards the electronic fuel injection system, but in depth I am going to cover about the internal control system architecture. Basically, this lecture series of this lecture will see about the internal control system architecture of an SI engine. Of an SI engine. If you will see here, the SI engine consists of a lot of parameters needs to be controlled, starting from the air-fuel ratio, throttle control, idle speed, ignition timing, knock control, turbocharger control. Like this, there are quite a lot of parameters needs to be controlled in case of a engine control. So there should be a need of a central coordination is needed in case of an engine control. That's why here they have been make the central coordination as an important variable. One of the variable is the torque. So whatever the requirement you as a driver or as a other system needed from an engine, everything will be converted into a torque demand. Like if you will see from here, driver torque demand is measured by means of a accelerator pedal sensor through the help of a accelerator pedal map, which is a two-dimensional map consists of a accelerator pedal position with corresponding speed and torque demand by the driver. This map is obtained from the engine test bed while calibration, while engine testing itself, or you can say the while development stage itself. This map will be stored. Like this, there are a lot of maps will be present inside the control system architecture of an SI engine. Like other than the driver demand, auxiliary system demand such as AC compressor has to be on, power steering pump, alternator. These are also need certain torque from the engine. So the certain output from the engine that will be converted into torque. Torque and such as other torque demand from the other ECUs like cruise control, electronic stability control, transmission control. Because while transmission control, gear has to be shifted or gear has to be increased or decreased. So at the time that torque from the engine has to be reduced or increased. So for that again the torque control module will be communicated towards the engine control module through the CAN communication, and it will give its request. This much torque has to be increased or this much torque has to be decreased. So that will be also included in the centrally coordinated torque demand. And other than that, engine system itself, like over speed limitation, whenever the speed is going beyond more than certain limit, at the time the speed has to be limited. Similarly, while startup or the catalyst heating, while startup you need to put a more fuel, and similarly catalyst heating at the early morning when the temperature is low, the catalyst will not be warmed up at a higher sufficient temperature. So in order to warm up at a certain temperature, so more fuel needs to be injected. So for that, again, that fuel injection fuel quantity will be correlated in the form of torque demand. Similarly, engine protection, idle speed, these are all the certain demands required from the engine. So these all demands will be connected towards this module called as a centrally coordinated torque demand and prioritization algorithm. So based on this coordination, which torque has to be attained first and which torque has to be attained second or lately, so it will be prioritized. So that priority has been given, and accordingly final torque demand value, like you might be able to see, the final torque demand value has been attained from this module, and it will be transferred towards the next module. So here in the next module you might be able to see there is a fast and slow torque realization. So there are two methods by means of, for example, if it is a say 70 Newton meter torque produced engine, now the torque is demand from the engine is say 23 Newton meter. So that is a very urgent one, or a very immediately it is needed, or very slightly slowly it is needed. So that will be based on priority, and again it will be controlled accordingly. If it is needed very fast, then immediately it will try to change the spark timing accordingly. If it is needed slightly low or in the next cycle, fast and slow means if it is the torque demand has to be achieved in the next consecutive cycle, or in the immediate after late 1 or 2 cycles. So that is we can able to differentiate the fast and slow torque realization method. And from there, according to the torque requirement, the information will be given towards the corresponding what do you say, the control module. Like in case of engine, there are a lot of control modules, or you can say the lot of actuators. Actuators are nothing but the actuating device which is converting the electrical signal into mechanical output. Like injector is an actuator, throttle is an actuator. Similarly, spark control, it's not an actuator, it is just an output. Turbocharger is an actuator. So each and actuator is controlled by a you can say the separate control module. For example, according to this torque demand, air and fuel has to be controlled. So airflow will be controlled by the electronic throttle control module, and again fuel will be controlled by the fuel control loop. For example, what are the parameters will be controlled in the fuel control loop means at what time injection has to be start, and at what time injection has to be stopped. It means that injection duration. Fuel cutoff in the sense if it is a 4-cylinder engine or a 8-cylinder engine, some cylinders has to be cut off. It means it has to be switched off, like a situation like whenever there is a deceleration, at the time some injectors has to be switched off. So that is will be called as a fuel cutoff, and that corresponding signal will be given towards the injector. Here the picture I have shown is the throttle body port fuel injection, PFI injector. The same principle will be applicable towards the GDI injectors. In that case, the injector will be located inside in this place, or that means inside the combustion chamber. And next comes to the electronic throttle control module, or otherwise we can say the ETC. Depending upon the torque requirement, the throttle angle has to be set, like 20 degree to realize that 28 Newton meter torque. So for the torque, this throttle control module will vary the throttle valve by rotating a motor. Here the throttle valve will be operated by a electronic throttle body. There are two different types of throttle body will be you may came across, like electronic throttle body and partially electronic or a mechanical throttle body. There they will use a stepper motor. Here in the electronic throttle body they will use a DC motor. And again, depending upon if any idle condition is needed, so again for that idling, this throttle angle has to be controlled. Again, this idle control module will communicate towards the throttle control module to set the throttle angle for a certain requirement. And next comes to the ignition module. If this is the speed and this is the load and this is the torque is required, this is the spark timing, like that. And again, knock control module. Knock control module consists of a knock detection unit. Knock detection unit is nothing but there is a presence of a knock sensor in the cylinder head. I hope you might be aware about what is meant by knocking in an SI engine or a detonation in case of a diesel engine. Knocking is nothing but a self ignition, or you can say the unwanted combustion, or otherwise a self ignition inside the combustion chamber. It will lead to damage the engine if excessive knock. So in order to reduce that knock, there is a presence of knock detection sensor, or you can say the knock sensor, which is nothing but a piezoelectric accelerometer. It will sense the knocking frequency, and that detection module will sense that whether there is a knock or not. If there is a knock, then immediately it will controls the either ignition module, or it can control the turbocharger module, or sometimes it can able to control the throttle module also. And the next module you may able to see is the turbocharger control module. Turbocharger control module is nothing but this portion is called as a turbocharger. The turbocharger is nothing but it is a device which is used to increase the or you can say the device which will compress the incoming air. Hence it will increase the amount of air entering into the cylinder. So it will consist of two components called as a compressor connected towards the intake portion, and another one is a turbine which is in the exhaust portion. This turbine is rotated by the exhaust gas. In turn, this turbine will turn the compressor part. So by means of knock has to be reduced to the turbocharger RPM. Again, the turbocharger module will vary the actuator present in the exhaust portion. So hence the turbine RPM will be reduced and leads to reduce the compressor RPM. So hence the intake air pressure will be reduced. So here I have mentioned only 5 to 6 control modules only. Other than this, there are other control modules also present in the nowadays engines, like VVT, variable valve timing control, EGR control. Like this, there are a lot of control modules also be present in the modern engines. And one more important control module in the bottom of the engine management system you may able to see is the diagnostic control module, which is nothing but it will monitor the entire operation of the engine control, and as well as the engine related sensors and actuator functions, hardware and as well as software wise. And if any problem is there in the engine operation, immediately it will indicate through the driver in the cluster through the CAN communication. Next comes to the as of now I have given a just introduction how the engine control system is being operated and what are the components present in the engine control system. Those things like EMS is a mixed signal embedded system interacting with the engine through the number of sensors and actuators. EMS is nothing but an engine management system. It is a mixed embedded signal. It will consist of an embedded device. It's nothing but a microcontroller, because it is controlling the engine operation through the number of inputs and output devices like sensors and another actuators. In addition, it includes the engine control algorithm, which we are going to see in detail in this lecture. Like this picture you may able to see is nothing but a torque based engine control. Like previous slide I have explained about torque demand manager. So here you may able to see the torque demand manager. This is centralized torque demand manager block, which will coordinates all the system torque demand, maybe external torque demand or internal torque demand from the engine startup, idling speed, all those things, and finally it will form as a torque demand. That torque demand will be converted into respective throttle angle output, ignition output, individual fuel cutoff, injection time, and this information will be goes towards the corresponding control module. Like throttle angle information will be going to the electronic throttle control module, ignition timing will be going to the spark control module, individual fuel cutoff, injection time, these will be going towards the fuel control module, and waste gate control is nothing but a turbocharger, it is going to the turbo control module. And if you will see, the research works has been carried in the past in the literatures, like a number of scientific literatures you may able to see. Mostly the work has been pertained towards the particular control module, like mostly the researchers has been university related research has been came across with the throttle control module alone, or a spark control module, or injection timing control module, like that. Individualized as a not a whole holistic approach, it is very rare kind of research has been done. Because this kind of engine control system has been designed by means of specified companies like Bosch, Delphi, Magneti Mirali, Continental, like those companies, and they are proprietary items. These they will not share this kind of control modules or the control programs towards others. So if you want to work on the entire system, then you may need the entire control logic. So that's why most of the research activities has been carried on the particular module. If you will see, my area of research has been concentrated towards the throttle angle module only, or you can say the electronic throttle control. Later on we will discuss that in a detailed manner. Like as I have said, these are the some of the basic modules within the engine management system which are coordinated with the torque control module, like a air fuel ratio control module, electronic throttle control module, ideal speed control module, ignition timing control module, knock control module, and similarly diagnostic control module. Like this there are some more lot of control modules such as camshaft control, turbocharger control, EGR, after treatment control also be present in the control systems, which may be present in the production vehicle engine management system. And again, one more thing, all the vehicles there is no uniqueness, whether some vehicle may use knock control module, some vehicles may not use a knock control module. So it is there is no predetermined what you call limit, but ultimately the predetermined limit is the emission. If you want to certify, if you want to launch a vehicle in a particular country, then obviously you need to be certified by those certified agency. Like in India, you have to certify with the ARI to satisfy the Bharat stage norms, BS norms. So if you want to satisfy those norms, then you need to have the certain kind of technologies. Like in order to satisfy BS4 norm for a diesel engine, you need a EGR system and as well as electronic fuel injection. So without that, you can't able to satisfy the Bharat stage 4 norm. So like that it will be vary from a engine manufacturer to manufacturer. So all these modules are run in parallel to the torque control structure in order to produce the desired engine output as demanded by the driver. Other modules are coordinated with the torque control module in order to accomplish the engine output for the torque demand. So basically these all modules will be operated in order to satisfy a one demand is nothing but the torque demand. So that torque demand has to be realized by the other modules. Like see, actuator control in a torque control module. As I already said, the actuator is nothing but a output device of the engine ECU. Sorry, these are located in the engine in the particular area. Like injector will be located either in the intake manifold or in the directly inside the combustion chamber in case of a GDA engine. Throttle valve located in the intake manifold, turbocharger control, ignition timing, or you can say the spark plug. So these are all the corresponding actuators. Like if you will see, driver is requiring something, or driver is requiring something means driver is demanding something from the engine. Demanding something means nothing but a torque. So similarly other system also demanding the torque. So whatever the demand has been arised, so the preference will be given and finally given as a desired torque. At the same time, actual cylinder charge will be calculated. How it will be calculated? Depending upon the engine speed and the as well as the presence of HFM sensor in the intake manifold. So depending upon these both conditions, you can say the actual cylinder charge will be calculated, and depending upon the desired torque as a torque demand, it will finally arrive this is the torque needed by the engine. So for this torque, corresponding throttle, wastegate, and you can say the corresponding injection, fuel, ignition has to be controlled. So this cycle will be repeated in the n number of times. Like next we will see the air fuel ratio control module, or otherwise we can say AFR control module. As I have already said, the torque control module will be giving the final torque demand. So depending upon the torque demand, this is the quantity of air is needed and this is the quantity of fuel is needed to achieve the required torque demand. So for the torque demand, to achieve it, the corresponding air and fuel has to be varied. If you will see here, there will be presence of a separate controller. See, like See this desired air fuel ratio coming from the which module? It's nothing but a torque control module. So for this desired control module, the base fuel pulse width will be calculated. The base fuel pulse width, or otherwise you can say the feed forward control. Feed forward control, it will measures the mass of air entering into the cylinder. So at this point, how much air is entered and what is the speed? I guess see here the speed information. So depending upon this is nothing but lookup table map or 3D 2D map. So for this speed and for this load, or you can say the amount of air, it will calculate that this much amount of fuel has to be injected. But at this point of time, the air quantity needed by the torque control module and air quantity arrived here, it may be differed. It will not be same, because whatever the air quantity needed by this module, it may lead to open the throttle control, but amount of air entering may be less, or probably it will be less. So for that only there will be presence of mass airflow estimator. It will estimate the amount of air entering into the cylinder through the help of MAP sensor and the temperature and pressure sensor present in the intake manifold. So now the fuel has been injected. So and again, for example, now for the corresponding air quantity you have injected a fuel, but it doesn't mean that all the fuel will be injected correctly or all the fuel will be injected actually. Some of the fuel will be form as a film in the intake manifold or in the valve or in the piston head or like that. So like you might be able to see here the fuel puddle in the intake manifold portion. So in order to compensate that, because in the present cycle some of the fuels will be accumulated over there, that will be carried over in the next cycle. So you have to compensate that. So for that only there is a presence of a fuel film compensator. It is nothing but depending upon a mathematical model. So once it is injected, now the combustion has been happened. Once the combustion has been happened, the EGO sensor, exhaust gas oxygen sensor, or otherwise it is called as a air fuel ratio sensor, or otherwise it is called as a lambda sensor, all are one and same. It will use a zirconium material. It is made up of a zirconium material. It will measure the amount of oxygen content present in the exhaust. Depending upon that, it will say whether the vehicle is the engine is operating in a rich mixture or a lean mixture or a stoichiometric mixture. So it will able to say if it is operating in a rich mixture, then in order to convert it into stoichiometry, amount of fuel has to be reduced. If it is operating in a lean mixture, in order to convert into stoichiometry, the amount of air has to be reduced. So for that only there is a presence of air fuel ratio observer. In this right side portion you may be able to see air fuel ratio observer. It will consist of a cycle delay and sensor delay. Cycle delay and sensor delay is nothing but once you inject a fuel in the intake stroke, it will take 3 cycles to measure whether that cycle injected fuel is a rich, lean or a stoichiometry. So that delay and a sensor delay, because the sensor may able to operate at this temperature range more than 230 degrees Celsius. So that is a sensor delay, and based on that it will be giving the value towards the controller. A controller, here the controller is, it might be a PID. Mostly in the production engine control unit they are using the PID controller. So this PID controller will get the feedback, and depending upon this feedback, again it will compare the required input, and depending upon that again it will vary the injector pulse width. This cycle will be keeps on repeating. Here the role of the PID controller, this controller is to compare the desired one and compare the actual one, and if the deviation is more, correspondingly it will vary the output, that injector pulse width output. Okay, so in this portion there are a lot of research works has been carried by many researchers. Instead of PID they have been putting the various controls like sliding mode control, adaptive control, neural network, like that. There are a lot of control approaches has been approached to vary the effective performance of this controller. Okay, so this is the working of a air fuel ratio control module. Next one is the electronic throttle control module. So the function of electronic throttle control module is nothing but depending upon the torque requirement by the torque control module, it has to vary the throttle angle in order to allow the sufficient amount of air to be entered into the chamber. Like you may able to see, as I have already told you, there are mechanical approach and the electronic approach. But right now what I am going to discuss is the electronic approach. In mechanical approach, and driver is pressing the accelerator pedal directly linked through the throttle valve and it will be opening. This is a mechanical approach. In case of electronic approach, when the driver is pressing through the accelerator pedal sensor measures the demand, and for the demand again it has been realized into torque. That torque will be converted into throttle opening. So this is the typical electronic throttle body. Here you will be able to see it consists of a motor. See, a DC motor. Through the set of gears it will be driving the throttle valve, and here a component called as a throttle position sensor, TPS. It will measure the actual position of the throttle valve and it will provide the feedback, and hence the closed loop control will be maintained. So here the controller is nothing but a throttle controller. Throttle controller will receive the throttle set point from the torque control module. For the torque set point, it will calculate the how much throttle angle needs to be opened, and that corresponding throttle opening angle is fed into the H-bridge driver circuit to drive the motor, and the motor will rotate the gears. It will to keep the throttle valve in the required position. Here you may able to see two springs. These springs are called as a limp-home springs. Limp-home is nothing but if there is any problem in the engine related application or the what you call the ECU related thing, if there is a power failure like that, then this spring will ensures to put the throttle in a default angle like 14 degree 15 degree usually. So it ensures that some minimum quantity of air is entering into the cylinder, so the vehicle will not be stopped, or you can say the engine will not be stopped. So that is the function of the limp-home spring. So I guess with this slide you may able to understand the throttle, how the electronic throttle is being functioned. This is the typical electronic throttle body. An electronic throttle body is a critical component which is located in the intake duct of an SI engine, and there is a need of added redundancy for its operation to ensure the safe and reliable operation. So these are the different components present in the electronic throttle body. This is the butterfly valve, like here you may able to see, and this is the throttle position sensor. The twin potentiometers will be present for the redundancy reason, and these are all the different gears, and this is the motor. So here why we need a separate control system for a electronic throttle control means it consists of a lot of non-linearities. Non-linearities are nothing but there are certain parameters which is affecting the actual position of the throttle valve. Like you may able to see, this is the required throttle opening angle which is coming from the torque control module. According to this, the controller, here inside the controller may be a PID, again like a sliding mode or a neural network based, any control may be applicable, but in production control unit they will be using the PID controller only. This controller will be present in order to handle the various non-linearities present, like limp-home spring is a non-linearity. Why it is called as a non-linearity? It makes the throttle in a default angle like 14.5 degree example. So if you want to open for a 16 degree, already throttle is open for a 14.5 degree. So you need to give the command for the again to open 1.5 degree only. So that is act as a limp-home non-linearity. And non-linearity is due to the production deviation, system parameter variations, and other non-linearity is caused due to the frictions. Because there are a lot of mechanical components like gears. Here you may be able to see this is schematic. A lot of frictions will be happened, and non-linearity is due to the airflow disturbance, time delay, and due to aging. These are all certain non-linearities which will makes the throttle valve to not to place in a required position, and it leads to create the error. And here you may able to see there is a presence of a throttle position sensor. This throttle position sensor will measure the actual position of the throttle valve, and again it will give the feedback to the control system to compare it and to provides an error, and hence again the based on that error the controller will provide the motor control signal which will be feeding towards the H-bridge driver circuit, and this will drive the DC motor. Next comes to the idle speed control module. Idle speed control module is nothing but whenever the driver is not pressing the accelerator pedal but the engine is still running, means, or you can say the gear is not engaged and the driver is not pressing the accelerator pedal, the engine is moved into idle. A typical idling RPM of an engines will be varied according to the type of the engine to engine. Like why this idle control system will be important means when the driver is not pressing the accelerator pedal, but still the throttle angle has to be opened and corresponding air amount of air has to be entered to ensure that the throttle angle has to be adjusted for the satisfying the idle speed. Like not only idle speed, like during the idling time the other accessories may be run in on conditions, like headlamp may be on, air conditioners may be on, power steering pump, electric window, battery may be charged, and other electrical accessories may be in on condition. So in order to ensure that this idle control system is an important one. The objective of the idle speed control module is to keep the engine speed close to the set point and at the same time prevent the engine stalling when disturbances the loads are applied or removed. So the torque control module is the basic one here. It will receive the input from this way, all the vehicle related information, and it will set the idle speed. So there is a particular requirement for the idling torque. Like if the idling torque is say 4 Newton meter, when at the time the AC is on, still the idling torque may be increased, like say 7 Newton meter. So for that particular torque requirement, it will torque control module will set the idle speed. So for this idle speed, there is a presence of idle speed controller. This idle speed control may be a PID, again it may be a PID or a neural network or a fuzzy logic, anything, but most probably we are using the PID one. And for to satisfying that speed, it will vary the amount of air and correspondingly the spark, and one more input it is left is the what you call the fuel. So that is being missed in this diagram. Okay, so it doesn't mean that fuel is not a part of idle control. Yes, fuel is a part of idle control, but it is missed. So in order to satisfy the amount of air quantity, again this will be going to the ETC module, and it will vary the what you call the amount of air entering, and depending upon the torque requirement, again the ignition control module will vary the what you call spark timing, and correspondingly the fuel control module, that is nothing but a injector, will vary the injection. So again this will be repeated, and the speed sensor will take the feedback, and it will give the feedback, and it will compare whether this idle speed, set speed, and the target speed and obtained speed are matched. If it is not matched, again this controller will try to vary the output. So the idle speed set point depends upon the various torque disturbances, but the load torque is not actually measurable, only predictable through the feed forward lookup tables or various disturbances. Like load torque means here the accessories. This is not measurable because each and every load cannot be measured. So it has to be predicted based on the lookup tables values. By estimating the load torque present to the engine by measured disturbances, one can calculate for a fixed air fuel ratio and the spark, the amount of air that is needed to maintain the engine speed for the fixed set point. A closed loop controller determines the compensation with the throttle and ignition actuators for engine's speed tracking error, and it is typically gain scheduled to operating conditions where non-linear maps are used to determine the gains. Here the gains are nothing but the controller gain. Whether if error is more, what kind of gain? If error is less, usually we will call it as a proportional integral derivative control, KP, KI, KD controller. So for that there is a presence of a lookup tables. Next one is the ignition control module. Ignition control module is also one of the important control system in the torque control module, because ignition control module, it does not have any controller, but it is only having the what I call a predetermined lookup table. Predetermined lookup table in the sense this particular lookup table you might be able to see here. Inside it will be there. If this is the speed, if this is the load, then this is the optimum ignition timing, ignition angle, otherwise you can say. The speed is coming from the which sensor? Yes, correctly, nothing but a crankshaft speed sensor. This load is nothing but the torque requirement. This torque requirement is coming from the what I call torque control module. So for that it will measures the, or it will gives the what I call the optimum ignition timing. But there may be other systems which is maybe affecting the ignition. Maybe the, as I have already told you, fast torque demand, slow torque demand. So at the time ignition timing has to be adjusted. So for that again this act as a correction factor, and it will be sent over here, and some it will be both will be summed or it will be added, and finally it will be given towards the what you called corresponding spark plug. Sorry, here it is mentioned as injection angle. It is wrong. It is nothing but a ignition angle. Okay. In torque control structure of an SI engine, for the demanded torque, the control signals are fed into the actuating parts such as throttle control, injection timing and ignition timing as shown in below figure. See, actually here it is supposed to come as the ignition timing or ignition angle. It is mistakenly I written as injection. I apologize for that. The superior ignition timing determines the significant quality and efficiency output from the engine. The ignition timing is evaluated based on the set values of the torque and other parameters like engine speed and actual engine airflow. So the actual engine airflow will vary according to the engine load. That's what. Okay. So this is a typical spark advance map. See here in the previous slide you may able to see that is a ignition timing map. So that is for a particular speed and particular torque. Again, for the same particular speed and some particular torque, amount of angle need to be advanced, because we will be calling it as a MBT, maximum brake torque will be attained at a particular spark timing. So again that will be varied according to this map depending upon the some correction factors like engine temperature, load, all those things. This is called as a spark advance. So first the ignition timing will be ignition timing will be calculated and it will be ignited, and again depending upon the situation the spark advance will be calculated and it will be added along with the previous cycle calculated ignition timing. Next one is the knock detection and control module. See, this is one of the important module. Why means knock is one of the important factor in an SI engine which leads to vary the compression ratio, because knock will be pertaining more in an SI engine because of the fuel property, and because of that we can't able to increase the compression ratio of the engine to more than certain limit. By increasing the compression ratio, I hope you might be knowing that we may get a better efficient output. So in order to go for a better higher compression ratio, this knock detection and control module is very much important. Like why means whenever there is a knock is pertaining, through the closed loop control you may able to reduce or you may able to remove the knock also. How means by varying the ignition timing, or by varying the throttle angle, or even by varying the what you call the turbo actuators. So comes to knock detection module, advancing the ignition timing by the ignition control module in the torque structure is one of the important factors for maximizing the output torque and fuel economy of the engine. Because depending upon the spark timing only, as I have already told you, MBT will be varied. Unfortunately, the optimum spark timing is often accomplished by the occurrence of knock in the combustion, and even it leads to damage the engine in extreme conditions. Therefore, a trade-off is necessary in engine control between the maximum sparking advance and avoiding the occurrence of knock. Most commonly, knock is defined to occur when it is audible. Knock sensing plays an important role in the knock control. Knock sensing is done by a separate knock sensor which is present in the cylinder head. A typical 4-cylinder engine will consist of a 1 knock sensor, and a typical 8-cylinder engine will consist of a 2 knock sensors. Otherwise we can say for a 1 bank there will be a presence of 1 knock sensor. Hence the knock control module consists of a knock detection and controller for controlling the knock phenomena. First the knock has to be measured. Knock is nothing but it's just an unwanted combustion and it leads to vibration of the engine. So but normally the engine will vibrate when knock is there or not there. But whenever the knock is there, that time that has to be identified correctly. So for that the accelerometer, piezoelectric accelerometer will be the continuous acceleration signal. But if the frequency of the signal will be crossed more than certain limit, then we will be termed it as a knock. The majority of the control algorithm therefore detects the resulting knock in the combustion chamber by means of different techniques. Many approaches have been applied to detect the knock, and each of its have own merits. Commonly applied techniques use in-cylinder pressure transducer, engine block mounted accelerometer, or ionization signals from the combustion. Like out of these three, in-cylinder pressure transducer, which is a very costly. The cost of the typical sensors may be more than a lakh. In-cylinder pressure sensor, so that is not a feasible one. And another one is the ionization signal. That is also not that much feasible as compared to the accelerometer. So the present production vehicles it will use the accelerometer only as a part of the what you call the knock sensing module. Here you might be able to see the knock detection module. The very first one is the sensors, maybe knock sensor 1, knock sensor 2, interface circuit. Through this is nothing but a signal processing, and it will able to put the filter, knock filter and processing. Here you may able to see, because knock filter it is continuously giving the accelerometer signal, that is acceleration signal. So once if it is crossed more than certain acceleration or more than certain frequency, that frequency will be passed to the filter, maybe a band pass filter, more than certain band, and that band will be related towards the knock. A knock control module, as you will see in the slide, consists of a separate signal detection unit to spot the knock from the accelerometer sensor signal as shown in the figure, which is composed of three main elements, that is the knock sensor, knock detector, and control strategy for executing in the controller. The traditional approach for knock detection uses a band pass filter and recognize the frequency band of the knocking from the normal noises of the combustion and the friction. Next, once the knock has been detected, it has to be controlled, isn't it? To limit the knock when it is detected, commonly used control approaches are retarding the spark timing, or by reducing the load, that is closing the intake throttle, or by controlling the wastegate in the case of turbocharged engines if it is equipped. Load reduction is used only if knock cannot be suppressed by delaying the ignition timing. See, if you will see here, this is the basic ignition map, which is already we have seen. Advancing the ignition after this. Okay, if a knock is persisting, knock detection, knock has been persisted, and knock detection has been done, and immediately the knock correction has to be done by varying the ignition timing. See, I'm able to get, see, this is the output of the base ignition angle. If knock is there, again it will try to reduce or increase, and still knock is there, again here one more control signal will be going to reduce, or it will vary the throttle, and again still it can't be able to control, again one more control signal will be passed towards the turbo control module, which is not shown here. Next, one of the important module, which is or you can say the last module of our presentation, which is the diagnostic module. As I have told you, there are a lot of different modules present in the control modules present in an engine control system. Because of the time restriction, I am not able to cover all those modules. I am covering very least modules, and this diagnostic module is one of the important module, which is we are going to see now. In order to regulate a superior engine system performance, more and more feedback control loops with embedded sensors, actuators, and controllers are integrated in the engine management system. Hence, an increasing in the complexity of the engine system and increased dependency on electronic engine control leads to embedded fault detection and diagnosis as an indispensable module in the engine management system. As because of the more and more sensors, more controllers, more actuators which has been put into the system, the diagnostic compatibility will be a major one, because if any fault will be arrived in any component or any system, it needs to be immediately noted towards the driver, and immediately it has to be rectified. While rectifying also, it is as it is electronically controlled engine, you can't able to locate the fault by a visibly or by a experience or by means of a feeling. If it is a mechanically operated engine, by means of vibration or by means of a driver feel or a technician feel, they may able to identify. But nowadays these electronically controlled engines becomes more and more complicated. It is very tough to identify all those problems as by manually. So for that we need a separate control module, or you can say the diagnostic module. So that module we are going to discuss in this section. Depending upon the type of system, unit or a sensor to be monitored, different strategies are employed in the diagnostic module, like a model based diagnostic, knowledge based, signal based, data based. A model based means a typical mathematical model including some inputs and output functions. If input is this much and output is has to be that much, if it is not more than that, or if it is not in the pertinent limit, then it will determine as a fault. Knowledge based, it is depending upon the prior knowledge of the physical processes used to ascertain when a fault condition has occurred. And next one is a signal based. Signal based is nothing but depending upon the sensor signal or a strategy, like if the sensor signal will be more than certain limit or less than certain limit, again it will act as a fault. And data based, a neural network can be used as a train a black box process model without having a detailed understanding of the physical process involved, and then is used to compare against the actual physical process. Like what I mean to say is that data are nothing but coming from the inputs coming from the sensors or in the internal part of the control system. So this will be trained in the neural network, and if it is more than certain limit or less than certain limit, then it will be termed as the fault, or it will be termed as a fault signal, and then corresponding mill lamp, or you can say the malfunction indicator lamp, will be indicated in the cluster, instrument cluster, which will indicate to the driver. Here I am going to cover only the model based diagnostic. In a model based fault detection approach, different methods can be applied, such as parameter estimation, parity equation, state variable estimations. The approaches of the model based fault detection involves mathematically describing the process, and model is employed to check the discrepancies between the different sensors. So here the mathematical relations, it will relates different sensors, and correspondingly it may able to produce the output. From this it is possible to calculate the internal process quantities, for example residuals, parameters or state estimates, which are called features. From this process quantities, fault can be detected. Then from the analysis of the difference or residuals, symptoms can be generated and subsequently used in fault diagnosis. When using residuals, the output is usually referenced to known as a threshold value. Exceeding this threshold value generates indication about the fault. So if there is a model, like if you will say like air intake air system fault diagnosis model, if that model consists of a intake air temperature, air quantity, air pressure, and it will finally output, it will give the limit of air quantity. If the limit will be more than certain threshold limit or less than certain threshold limit, then it will be indicating there is a fault in the intake system. So for that it will indicate the malfunction indicator lamp. Like actuators, engine, sensors, and this is the what you call model where it may able to nominal behavior. Depending upon the signals and process, it will generate the residual, and it will detect it, and finally it will give the symptoms as the fault. So depending upon this fault, the system or the driver has to note down this fault, and he has to take the vehicle to the service center, and he has to recover it, or you can say not recover, to replace the fault or rectify the fault. So these are certain discussion about the right now we have discussed about the certain control system architecture point of view. Here now I will conclude about this lecture by giving some future perspectives of engine control research, like in what direction the future engine control research can be moved. The first point is nothing but an open architecture based engine management system. As presently in the very beginning I have pointed out, all the ECUs, all the engine control architectures are proprietary, belong to the certain manufacturers. The open community like university based research are not possible to develop in a full-fledged manner. So by means of developing an open architecture, we can able to work on more contents related towards the engine control system, and hence we can improve the control system perspective point of the engine. And next one is the, since nowadays we are using the torque control module as a central part of the engine control, like what I mean to say, that whatever the inputs you are giving to the engine ECU, everything will be converted into torque, and for the torque output will be released, but whether the torque will be attained or not, it is not measured. As of now, some of the manufacturers, they might be using some estimator algorithm for estimating the torque, and it will comparing with the feedback. So in order to overcome that, we can develop a low cost torque sensor for estimating the torque produced by the engine. Next one is that because of the fuel scarcity and the stringent emission norms, the hybrid vehicles are going to dominate the future mobility. So in those cases, hybrid vehicles is nothing but a combination of SI engine plus motor or a two source. So in those cases, the both sometimes it will be operated in the engine, sometimes it might be operated in the motor. So those mode switching has to be done in a proper way, and still more some amount of research can be done in those area. And one of the major important factors, present production EMS architecture uses a PID controller along with the number of parameter maps, values, time delays, like it will be stored in the lookup tables. These lookup tables has to be generated during the calibration, that is during the engine testing phase, or you can say the development phase. So this is the most time consumed and most cost thing. So instead of that, we can go for a model based control by replacing a lookup table with some models. So that will lead to give a better save in the cost. And next one is, in order to save the time in calibration process, we can able to go for a some kind of a calibration reduction time software also we can able to propose. And next point is the various sensors present in the engine control system. So some of the sensors can be replaced by means of a soft sensors, or add-on sensor can be added to the particular sensor by means of going a soft sensor. Soft sensor is nothing but a sensor developed in the program, a soft one. So that is also called as a virtual sensor. That is also one of the future perspective of the research. And of course, as there are a lot of complexities arise in the diagnostic system, presence of many electronics and software components, there needs to be trained technicians to handle many issues related to the fault diagnostics. So the next generation diagnostic system will be integrated in the through the cloud computing approach. Like if any fault is going to happen in the engine, through the cloud server, this health of the vehicle or the health of the system can be monitored from there by the manufacturer itself, and they can able to intimate to the drivers this component is going to fail at this time, so you please aware about that. So that is also one of the possible thing to providing the cloud computing based diagnostic system. And the last point is nothing but the as the throttle as the engine control is a non-linear phenomena which will varies its operating characters continuously on real-time basis. So as adaptive or a smart control system, in order to know the what is the road condition, what is the atmospheric condition, whether the product is aged or not, so it will be everything will be updated in a real-time manner, has to be determined. So that kind of control system also is needed for the engine control system in future. Basically this presentation has been came across with one of my the review paper which our team includes myself, Professor B. Ashok, Dr. S. Denish Ashok, and Dr. C. Ramesh Kumar from Department of Automotive Engineering. We have worked for last 1 year for this writing a research paper in this area of review on SI control system architecture of SI engine management system. By reviewing nearly about 230 plus articles, we came up with this review paper, and we successfully published in this paper in the annual reviews in control, which is having the impact factor of 2.5, is a part of the elsewhere, and it is also part of the IFAC group. IFAC is nothing but a International Federation of Automatic Control Group, which is one of the renowned group, and it is one of the renowned journal, and it is very, we have gone a very stringent review for publishing this journal, and finally we successfully able to publish this paper, and this presentation is based on the that review paper only. So if you want to know more about SI engine control system architecture, please go through this review paper, and these are all my contact information. Thank you very much for your peaceful and wonderful listening. Thank you very much.